Hi dears, today we can see CSIR NET Max and linear algebra. First question, let M4 of R be the space of all 4 by 4 matrices over R. Let W equal to set of all matrix Aij belongs to M4 of R such that summation I plus J equal to K, Aij equal to 0 for K equal to 2, 3, etc. 8. Then we have to find the dimension of W. So for that, dimension of W is equal to dimension of M2 of R minus linearly independent conditions. Okay. So dimension of M2 of R, how we have to find means just the condition is given here, summation I plus J is equal to K, Aij is equal to 0. So this you can see that 1 plus 1, right, which is equal to what here? K. Here you can say K. K is equal to 2. If I am taking 1 plus 0, it will be 1, but it is not there. K. So 1 plus 1 is equal to 2. So that means you can write that A11 that is equal to 0. Similarly, summation 1 plus 2 is equal to 3. Right? Aij which is equal to A12, that is 1 plus 2. That means also equal to 0, or 2 plus 1 that is also equal to 0. Similarly, you can see for A13, A31, A14, etc. So the possibilities are 16. Okay. So 16 possibilities are there. Minus linear independent conditions K is equal to 2, 3, 4, 5, 6, 7, 8. That is 7. Right. So which is equal to 9. So option 3 is the right one. Option 3 is the right one. Let's see the next question. Let W B be the vector space of dimension 3 over F. Let T from B to B be a linear transformation given by the matrix A is equal to, with respect to the ordered basis B1, B2, B3 of B, then which of the following is true? So here T from B to B is given by the linear transformation. So the formula is T of B is equal to A into B. So A is this value, V is V1, V2, V3. Accordingly, we will get T of V1 is equal to V1 plus V2 minus 2 V3. T of V2 is minus V1 minus 4 V2 plus 5 V3. T of V3 is 3 V2 minus 3 V3. Okay. Let's see the option wise. So T of V3 is equal to here 3V2 minus 3V3, which is not equal to 0. So our option A is the wrong one. Option A is wrong. Let's see the B option. V1 plus V2 plus V3 equal to 0. So T of V1 plus T of V2, that is the linear independent condition. Linear transformation condition. T of V1 plus T of V2 plus T of V3. Substitute all these values there. You can find, so then V1 minus V1 get cancelled. Then plus V2 here minus 4 V2 here 3 plus 4. So this get cancelled. Again here minus 2 plus 5, that is plus 3. So here minus 3 get cancelled, so 0. So option B is right. Okay. Let's see the third option. T of V1 plus V2, that is T of V1 plus T of V2. Substitute these values. Here V1 minus V1 get cancelled. Here 1 V2, so here minus 3 V2, then minus 2 plus this 3 V3, right? So it is not equal to 0. Here option C is false. Okay. So similarly, you have to check for option D. So for this question, option D is the right one. Let's see the third question. Which of the following matrices are diagonalizable? Here it is given. So we know that if the eigenvalues are distinct, then we can say that the value that is diagonalizable. Not only that, together with you have to check that algebraic multiplicity is equal to the geometric multiplicity. So, and one condition you have to remember that not all the upper triangular matrices are diagonalizable. Okay, that also you have to see that. So here 1, 1, 1. Okay, the first one. So lambda cube minus trace of A into lambda square plus minor of lambda. So minor you can easily find by using this. So first 1 into 1. So that it is 1 here. Then you can check this 1 into 1. That is 1. Then you can check this one. These values. So it is easy to find them. So 1 into 1 minus 0, like that. Okay. So that you will get here lambda minus determinant of A is equal to 0. So that lambda cube minus 3 lambda square plus 3 lambda minus 1 equal to 0. So from here I can understand that 1 is the sure eigenvalue. So lambda equal to 1 and use the synthetic division method. Write the coefficients 1 minus 3, 3 minus 1 and put this 1. The first number always be 0. So 1 plus 0, 1. 1 into 1, 1. So here minus 2 into 1, minus 2. So here 1, 1 into 1, 1. So this will be 0. Okay, here should be get 0. So that this value is 1. Okay, one of the eigenvalue. Let's find the other one. So lambda square minus 2 lambda plus 1 equal to 0. If I have to reduce like this, lambda square minus 2 lambda plus 1 equal to 0. So by factorizing this, we will get lambda equal to 1 comma 1. So the first one is 1, second and third is 1. So all are not distant. So we can say that it is not diagonalizable. So if it is distant, then we can say diagonalizable. Together with, you have to see that algebraic multiplicity and the geometric multiplicity for the sureness. So this is the second one. So lambda cube minus lambda square plus, just find the cofactor. So this is the first cofactor, then the second cofactor, and the third cofactor you can find by using this. Just multiply, you will get this, okay? So that lambda cube minus lambda square plus lambda minus determinant A. Determinant A is 1 is equal to 0. By doing the calculation, we will get lambda equal to 1 and lambda equal to plus or minus 1. Here you can see that all are distant. If it all are distant means then no problem. Directly you can write that this is diagonalizable. If some values are distant and some is not distant means you have to check for the algebraic multiplicity and the geometric multiplicity. Okay, if it is all distant, then it is diagonalizable. Let's see this third one. So lambda cube minus trace A plus cofactors of the terms lambda minus determinant A is equal to 0 and use the synthetic division. You can find the values of lambda are 1, 1, 2. Here you can see 1 comma 1 comma 2. 2 is the same, the other one is different. So from these cases, you can find the algebraic multiplicity. So here algebraic multiplicity of 1 means how many times 1 is repeating 2 times. Algebraic multiplicity of 2. Algebraic multiplicity of 2, how many times it is repeating? Only 1 times it is repeating. Okay. Let's check the geometric multiplicity. If it is both are equal, then it is diagonalizable. So geometric multiplicity of 1. The formula here is n minus rank of A minus lambda I. Here lambda is 1. So 1 into I. So which is equal to 3 minus rho into, this is the value of A. Okay. So what I have to do is minus I. So here minus 1. Yes, minus 1. Here minus 1. Here minus 1. So that I am getting here 0, 1, 0. Right. So that 3 minus rho of here 0, 1, 0, 0 minus 0, 0, 1 minus 1, 0, 0 minus 0. So number of non-zero row is only 1 row. So 3 minus 1 which is equal to 2. You can check here algebraic multiplicity of 1 and the geometric multiplicity of 1 is also 1. Okay. Then we have to check the other one, that is algebraic multiplicity of 2. And what about geometric multiplicity of 2? The formula here is n minus rank of A minus lambda. Here lambda is 2y. So this is A, then minus 2. Okay, minus 2. So that you are getting minus 1, 1, 0. From this you can see that number of non-zero rows is 2. So 3 minus 2 is equal to 1. Here algebraic multiplicity of 2 is 1. And here we are getting geometric multiplicity of 2 is also 1. So we can say that it is diagonalizable. Okay, option C is diagonalizable. Now you can see what about option D. That is the fourth option. Here you can see that this is an identity matrix. You can replace row 1 and row 3. Okay, so that it will be 1, 0, 0, 0, 1, 0, 0, 0, 1. So always the identity matrix is diagonalizable. So according to this question, option 2, 3, 4 are diagonalizable. Let's check the next question. For T belongs to R, define M of T is equal to matrix 1 T 0, 1 1 T square 0 1 1. Then which of the following statements are true? So determine M is a polynomial function of degree 3 in T. Determine M equal to 0 for all T belongs to R. Determine M is 0 for infinitely many T, and determine M is 0 for exactly 2T belongs to R. So first we can find the determinant M. So determinant M, we are getting 1 minus T square minus T. So which is definitely not a polynomial of degree 3, because this is a polynomial of degree 2. So option A is the wrong one. Let's check determinant M is equal to 0. So determine M equal to 0, 1 minus T square minus T equal to 0. By solving, you are getting minus 1 plus or minus root 5 divided by 2. So this is belongs to R. But if I am putting T is equal to 1, what about this one? Whether I am getting this value is equal to 0, 1 plus 1 minus 1, which is equal to 1, which is not equal to 0. So here it is, the B option is for all T belongs to R. Here I am to T is equal to 1. 1 is the real number, but I am not getting that value is equal to 0. Okay. So option B is the wrong. Similarly, infinitely is wrong, but exactly 2 value, the determinant is 0. Here you can see that exactly for these two values only this value is equal to 0. If I am putting this value, these are the roots, right? So these two are equal to 0. So we can say that option D is the right one. Determinant M is 0 for exactly 2 T belongs to R. Next question. Question number 5. Let A be the 4 by 4 matrices. Suppose that the null space N of A is equal to set of all x, y, z, w belongs to R4. X plus y plus z is equal to 0, and x plus y plus w is equal to 0. So what about these values? So we know that N of A is given here. X, y, z, w belongs to R4 such that x plus y plus z equal to 0 and x plus y plus w is equal to 0. Right? Okay. So that which is equal to set of all. Here you can write that z is equal to minus x minus y, and here w is equal to minus x minus y. Right? So that which is equal to, if I am putting here y equal to 0, what this become happen? Here you can see x, y is 0. So that here this become minus x minus 0. So that z place is minus x, and again here I am putting y is equal to 0. So that I am getting here also minus x. If I am putting y equal to 0, what this happen? You will get first I am to y equal to 0. Now I am taking x equal to 0. So that this gets us 0, y. Then again here I am putting 0, so that minus y. Again here I am putting 0, so that is minus 1. So what about the base spanned by this is, which is equal to 1 comma 0 comma minus 1 comma minus 1, and then here 0 comma 1 comma minus 1 comma minus 1. So option D is not a basis here. See here, this is not a basis, so option D is wrong. Let's check the, so N of A is given on the question is what? It is a null space. So what about the dimension of null space here? Dimension of null space N of A is equal to 1, 2, right? So which is equal to 2. Now rank nullity theorem, you can use it. So that rank, according to rank nullity theorem, we have that which is equal to rank plus nullity, right? N is equal to rank plus nullity. N is equal to rank plus nullity. So here you can see n value which is 4. Okay, 4 given on the question. So order is 4. Then rank plus nullity. Nullity here is 2. So rank is equal to 2. So here rank equal to 2 is the correct option. So here option C is wrong. Rank is wrong. But here we know that rank can be written as dimension of column space, or you can write that rank is equal to dimension of row space. Okay. So here we have rank is equal to 2. So dimension of the column space is equal to 2 is the right one. So option B is right. Option A is wrong. Okay. Thank you.